All right, so this is the unit on randomized algorithms, and we are going to do a problem called unlocking files. So this is one kind of problem that you'll see in randomized algorithms. It's very similar to quicksort. In fact, a lot of the problems, the more harder problems that you'll do will be the ones that are similar to quicksort. But I'll be honest, you won't really see these problems on the homework or exams because they are mathematically hard to analyze. Now, if you take the class in the fall with Avi, you have a ton of these homework problems, and you have these entire pages of just hard probability calculations. But in the winter, you don't really have that. Okay, but just in case they give you something like this on the exam, I'll just quickly demonstrate how you would do a problem that is very similar to quicksort. All right, so in this problem, you have a bunch of computer passwords, and you have a bunch of files. Okay, so let's draw the files and let's draw the passwords. So let's say our files are, these are our passwords, and these are our files. Now, so this array is F, and the password array is P. Now, the order of these is arbitrary, so it's not that these passwords and files are lined up in the right order. They're in some arbitrary random order. Okay, now each file, so if you test a password on a file, you'll either successfully unlock the file or the computer tells you that the password is either smaller or larger than the password, than the file's true password. Okay, lexicographically just means like alphabetically. You're not allowed to test the passwords with each other, and you're not allowed to test the file's passwords with each other. So you can only compare a password in a file. You can't do password-password comparisons. You can't do file-file comparisons. And then you want to design a randomized algorithm that matches each file to its password in expected O of log and log n time. All right, so going back to the idea of reverse engineering the runtime, we see n log n expected runtime. First thing you should be thinking of is quicksort. Right, and it sort of makes sense, right? Because this problem, we have a lot of these like lexicographical orderings. So it does make sense that we want to do some sort of sorting. Right? If P and F are both sorted, then that makes the problem easy, right? Because if P is sorted by the lexicographically, and then if F is sorted by like the file's passwords, if they're also sorted lexicographically, then you would be done because you can just match P and F like one by one. So index 0, index 1, you just match them like that, and you would have all the files unlocked. All right, so quicksort is definitely something we want to think about. The issue is that we can't really just directly sort P. Right? And you can't just directly sort F because you can't compare files with each other or passwords with each other. What we can do is we can compare a password with a file. So let's actually just try it out. Let's think about what happens when we compare. Let's take this password. Let's compare it to the other files. All right, or any file. What would happen is that you will be told that the password is either less than or greater than or does unlock the true file. Right? So in fact, you can actually split this files into 3 sections, right? Section 1, which is, so let's call this element P of I. So P of I is lex smaller than F of J. You get the actual file. So P of I unlocks F of J. And then you get one more section, which is P of I. P of I lex greater than F of J. Okay, so this is kind of like a partitioning, right? Kind of like in quicksort, we partitioned it across a pivot. The key difference here is that you don't like when we did this pivoting, we didn't have access to this thing, right? In quicksort, you would usually take this element I'm drawing an arrow to. You would take that element and then you would compare it with all the other elements to do that partition. Here, we don't have a specific file that we're partitioning across. Instead, we're using a password, right? Using that password, we implicitly know what the file is, and then we're partitioning across that file implicitly. Right? well, not implicitly, but we don't know what the file is. We just know what the password for that file is. And then we can use that password to do this partitioning into 3 parts. Okay, now we have the files partitioned. Right, that seems like one step to achieving our goal of sorting the files. We might also want to try to sort the passwords. How might we do that? Well, we can do the same procedure, right? Well, we know that this file, this file is like this file can be partitioning the files we're partitioning across that file. So we can use that file to partition the passwords. Right? We can get this. So this was our P of I, right? The P of I that we chose. It's going to be matched directly to the F of J. While here we now have here where we have F of J. Well, passwords like smaller than F of J's password, and password less greater than F of J's passwords. Okay, yeah, so just by doing this where we take a file and we use that to, we take a password, we use that to partition all the files. Then we use that file in the middle to partition all the passwords. Now we've partitioned both the files and the passwords into 3 groups, right? We know that these 2 pivots that we chose, they're going to be matched to each other, right? Because we just showed that P of I unlocks F of J. Now, we also partitioned these into 2 sections. And we know that all the passwords on the left side are going to be matched to the files on the left side. Right? Because we showed that both the password and the password that's required to unlock the file, the fact that they're on the left side means that they're both lexicographically smaller than the pivot password. Right? And similarly, on the other hand, all the files on the right side have to be lexicographically greater. So we've narrowed down our problem. We've simplified our problem to be, we now have a smaller subproblem, right? We now have, it's the exact same problem. Each, the blue circle and the purple circle are exactly the same problem, right? You have a bunch of passwords, a bunch of files, and you need to match them to each other. What we did is we broke that into a smaller array of passwords and files. Okay, so we made progress. That's kind of what we want to do in recursion, and we can now just make 2 recursive calls. All right, so let's just quickly write the algorithm for this. Def unlock files, F and P. Now we don't know what the base case is yet. Let's worry about that later. We choose a random pivot. So random element or pivot, let's call it pivot password. So it goes random pivot, random password from P. All right, and then now we can do the partitioning, okay? And I'm just, I'm a little conflicted about whether or not to use the subroutine. There is a subroutine called partition. Technically, we're doing a little bit different than what partitioning does, but okay, let's just use partition. So what we're gonna do is we're gonna call partition. Okay, remember that's a subroutine. And what we're gonna do is we're gonna pass in pivot password. And we're gonna ask to use that to pivot on, to partition F. All right, and then we're just gonna write a little comment saying that we're gonna use pretend pivot password and F are our passwords to be compared using computer. Okay, because we are slightly modifying partition, and like honestly, if this was like on a homework, I would write out what your new partition function looks like. But if this is like on an exam, or if I'm just being lazy right now, I think writing partition is probably fine. Right, and then once you partition outputs 3 things. It outputs the left. So I'm going to call that left files, the pivot file, and then the right files. Okay, that corresponds to these 3 sections. That corresponds to left file, pivot file, and right file. All right, now once we have that, now we can partition the passwords. Right, we use that pivot file to partition the passwords. Partition pivot file, we partition the P's to get the right files, or to get the left passwords. We don't really care about the pivot password because we already have that, and we care about the right passwords. All right. Now what we can do is we can simply just make two recursive calls. All right. We can say files left file result, and left password result is a recursive call, unlock files on LF and LP, and then right file result and right password result. That's unlock files, the right files and the right pivot. No, not right pivot, right password. Right, and then so we made two recursive calls. That's the blue and the purple. And then once we get those, we'll have the passwords being sorted and the files being sorted, and we can just concatenate them together. So we would say return. So for the files, we want to put the left file, then we put the pivot, then we put the right files. R. So that's the first return value. And the second return value, let's do the right files plus the pivot file, pivot password, I guess. Left password result, the pivot password, and then the right password result. All right, there we go. All right, so two return values. That's essentially the two arrays. Once you sorted each side of the partition, you concatenate them together. That's what I mean by the plus. Not comma, plus. All right, and let's think about the base case. Well, the base case happens when both have size 1, right, or size 0. So if length of f, they're going to be the same size, so it doesn't really matter which one you check. If they have length 1, then return the files, the files and the passwords. All right, and that's our algorithm. Now, this is essentially quicksort, right? Like you just look at the pseudocode, it's like quicksort. The only difference is the partitioning, where we have two partition steps. We have to partition the passwords and the pivot, and then the files, and then we pass in both arrays inside each recursive call, rather than in quicksort where you just had one array that you partitioned and you passed through each recursive call. All right, so you might expect that the runtime analysis is going to be pretty similar, and in fact it is, and it's sort of complicated, right? It was the runtime analysis you saw in class. Let's just quickly walk through and recall what the whole deal about the runtime analysis was. All right, so the runtime analysis focused on analyzing what is the expected number of comparisons, right? And we had this indicator variable x sub ij to denote whether or not two elements would be compared with each other. All right, now here we're not really comparing the elements with each other, right? We're comparing a file and a password. So just to make our notation easier, let's let p star and l star, these are the passwords or files in lexicographical order. So let's suppose we sorted them. Okay, we're not actually sorting it, but just to make the analysis easier, we're going to use indexing notation, assuming that they are sorted. Okay, and then our indicator variable x sub ij, rather than from lecture where this would represent whether or not element I and element j were compared, we're going to say this is indicator, which is 1 if we compare p star f, this should be f, sorry, f star I is compared with p star j. Okay, so we're going to have an indicator variable about whether or not one, like the ith file, is compared with the jth password. All right, yeah, so these comparisons are what dominate the runtime. It's kind of like a lecture where we sort of alluded to the fact that the comparisons is essentially the runtime, right? All the other steps in this code Well, we will talk about, yeah, in partitioning, that's comparing the files with the passwords. And then all the other steps about like concatenating the arrays, those are significantly, like those are not really important in the runtime. The comparisons are the most important part of the runtime. So we're just going to focus on the comparisons. So our goal is to try to sum how many comparisons happen. We want to sum the expected value of ij, right, for all I and j such that I is not equal to j. Because we might compare the comparisons we want to do are, we want to calculate the comparisons where I is not and j, yeah, for some file I and for some password j. I does not equals to j. Yeah, we're gonna write I is not equal to j because the comparisons of when I is equal to j is not like, there are like a fixed number of them, and that number is, it's gonna be at most n, right? We're gonna compare each file with its actual password n at most once. Okay, I suppose you could write like just do the sum of all ij, and then that's equal to, so there's three terms, the expected value of sum I equals j. So I guess that's just except I sum of k x k k, plus it's the sum of when I is less than j, x I j, and plus the expected value when I is greater than j. Okay. All right. So we said that this value was going to be, we said that this thing, right, each term is at most 1, so this entire term is at most n. So not super important because the other terms are going to be larger. So let's focus on one of these terms. What is the summation of I less than j of xi sub j? So to calculate this value, we want to think about what is the probability that, so this is the files, this is the passwords, that, let me use the color coding. What color coding did I do previously? I made the files red. Okay, so let's make the passwords. All right, so these are if f and p were sorted, right? And we're asking what's the probability that the file at index I is compared with the file at index j. Right, what is that probability? So that probability, these two elements are compared if this element is picked as a pivot before any of the elements in the middle are picked as a pivot. So, okay, because think about the logic here. If this red element is picked as a pivot, then we're definitely going to compare f star and p star, right? Because then when we do the partitioning step, we're going to compare every password with f star. So we are going to compare this green element with the red element. The issue is what might happen is that if we pick a pivot somewhere in this blue region first, before we pick the red one as a pivot, then what's going to happen is we're going to compare all the green elements with the blue element. And then what's going to happen is that they'll be split into two different recursive calls, right? Because if we partitioned according to some element in the blue, then we would be partitioning across the blue, like this. And in that case, the red element and the green element would end up in separate recursive calls. Okay? And if they end up in separate recursive calls, then you will never compare them ever again. So x sub ij is equal to the probability that f star of I is picked as pivot before before all the elements in the middle, and all the blue elements in the middle. So now let me just color code this so it looks easier to read. F star of I is picked as the pivot before the blue stuff. So the blue stuff is I plus 1 all the way to f star of j minus 1. These are all the elements between the red element and the green element. Okay, similar to the analysis in lecture, the only difference is that in lecture, the green element and the red element were on the same array, but now they're on different arrays. But that doesn't matter because when we pick those pivots, the only thing that matters is that we are picking the pivot in, we want to pick the pivot in the blue. Well, we want to pick the red pivot before we pick any of the blue pivots. I'm thinking about if there's an off by one issue here. I think even if you pick the, if you pick the jth element, like this element, the green element here, I think that will also cause the red element to not be compared, right? Because imagine what happens if you pick this green element, the f sub j star. So I think I have to include f star j. Right? Because if you pick that element, then right, once you compare f star j to p star j, you're going to realize they unlock the password unlocks the file. So you will then, when you make the recursive calls, right, these two, the green elements, don't belong in any recursive call. So then the red element never gets compared with the green password. Okay, so we're gonna say that this probability is equal to the probability that the red element is picked before any of the blue elements or the green element. Okay, now each of these elements are equally likely to be picked first, right? Because we're just randomly picking pivots. So how many total elements are there? There are, so it's from I to j. So there are j minus I plus 1 elements. And then how many, what's the probability that we successfully pick the red one before we pick any other one? That's 1, right? Because there's one possible success, the red one, out of all the possible choices, j minus I plus 1. All right, and then, so now we can calculate this expected value we wanted was expected value of x of ij, which is the expected value of 1 over j minus I plus 1. All right, and then if you solve this, well, actually, this should be expected value. So yeah, we already calculated the expected value was this expression. So when we did the summation, the expected value of the summation of xij, I is less than j. That is equal to 1, the sum I less than j of the expected value of x and ij. All right, and then, oops, sorry, I forgot to substitute it in again. J I over j minus I plus 1. All right, and then so you can plug that into here. This is sum of 1 over j minus I plus 1. And then this other case is like, it's literally the same example, but we just flip the green and the red so that the green appears first. And then you want to calculate the probability that you pick anything between them before you pick the red one. So that's still, this one is a similar expression. I over greater than j, I minus j plus 1, right? Except the only difference is that the index I is now greater than the index j. All right, now you showed in class that if you sum these up, you get n log n, right? There's a whole complicated math you can do, something about Taylor series, but that's not super important for this class. You just have to know that you see expressions like this where you have sums over 1 over something in the denominator, you know that that sums to n log n. So this, by showing these expressions, this shows that the overall answer is equal to O of n log n. So that shows that the expected runtime is n log n. Okay, yeah. So this is what you would have to do on an exam if you had to prove something like this. It's unlikely you'll get something like this because it's hard to prove. And algorithms that are based on quicksort are usually challenging. So you might not get a problem where you have to design a randomized algorithm that's recursive, but you might have to, maybe you might get a question which is like, you want to run quicksort, but you modify it just a teeny bit. So kind of like this question, right? This would be like a fair exam question, with the only exception that you probably won't be asked to analyze the runtime, because that is tricky, because you have to do all the expected value work. And on the homework, I don't think they've assigned any problem like this. So I would not expect a problem like this to appear on the exam. The other problem, though, the other problem that is in the other video, the random integers from random bits, this is on the homework. This is homework 3, problem 2. So make sure you understand this other concept. All right, but anyways, I hope this was helpful to understand most of what was covered in lecture on lecture 5, the one on quicksort. Yeah, unfortunately, the answer is that this math is not that important. All right, well, hope you enjoyed this video, and I'll see you next time.